Hello and welcome back. This is Lesson 7 from the series Applied Statistics Using Programming. My name is Dr. Ian and I'm going to explain today about hypothesis testing. In Lesson 7, we talk about one-sample hypothesis testing, and in Lesson 8, we talk about two-sample hypothesis testing. This video is focused mostly on the theory of one-sample hypothesis testing. The next video, Lesson 8, is focused on the theory of two-sample hypothesis testing, and then we will practice with both one-sample and two-sample hypothesis testing using R together. So if you're interested in the R programming portion of this lesson, please skip ahead to a future video. If you are interested in learning about one-sample hypothesis testing theory, then stick around and let's get started right now. One-sample hypothesis testing is used when we want to test whether our assumptions about the population are accurate or not. The contents of this video are logic of hypothesis testing, type 1 and type 2 errors, decision rules and critical values, testing a mean with a known population variance, testing a mean with an unknown population variance, and finally, we'll conclude with a very brief discussion about testing a proportion. So what is the logic of a hypothesis test? An analyst or researcher makes assumptions and proposes testable theories about the values of key parameters of a business or social or research environment. Those assumptions are called hypotheses if they can be tested. So each hypothesis is tested against observed data. In other words, we have an assumption about our population, and we use data to check whether our assumption is accurate or inaccurate. If a hypothesis has not been disproved, in spite of rigorous efforts to do so, the business may operate or the researcher may operate under the belief that the statement is true. In other words, the purpose of a hypothesis test is to test whether our assumption is not true. The analyst states the hypothesis in a format that can be tested using well-known statistical procedures. What are we testing to do? We're testing to see if our assumption is false. Why don't we just test if our assumption is true? Well, we can't know the truth, but we can see if data supports or doesn't support what we assume. If data supports what we assume, it doesn't necessarily mean we're correct, but it doesn't mean that we're wrong. But if our data looks like it does not support what we already believe, our assumption, then we might assume that maybe our assumption is wrong because the data is not supporting it. Therefore, hypothesis testing is focused on disproving the assumptions that we have. Those assumptions, in statistical sense, are assumptions about the parameters of the population. What is the average of the population, for example? When data are found to be inconsistent with the hypothesis, the data doesn't match what we expect, the hypothesis is either discarded or reformulated. Either our assumption is wrong or we need to adjust our assumption slightly if the data doesn't support what we assume. Sometimes hypothesis testing can be an iterative process. Usually, we get an idea, we formulate a hypothesis about that, we get some data to check, we find a test statistic using the data that we gathered, then we compare our test statistic to that test statistic is comparing our sample to what we assumed about the population. Then we make a decision depending on how our test statistic either supports or does not support our initial assumption. After we make a decision, we might revise our ideas, particularly if our assumption was untrue. This can be an iterative process because we may learn new things about our population that we're testing. So for example, if we gather data and find that our test statistic is very close to our assumption, then we may be making a decision that is not very different than our normal behavior. In that case, perhaps we would be finished with hypothesis testing. How many iterations of hypothesis testing depends on how complex the hypothesis is and how well formulated it is. In other words, how many locations do we need to test? How many groups of observations are there? Let's say we make an assumption about the satisfaction of customers at McDonald's. Well, let's say we assume that 80% of customers who go into McDonald's are satisfied. Maybe 20% are dissatisfied. How would we test that assumption? Well, first, we would have to test different locations because perhaps locations in one country are very different than locations in another country. If we're looking at McDonald's in a specific country, we might also consider different types of consumers: children, adults, elderly. As you can start to imagine, our hypothesis, which seemed simple at first, do people like going to McDonald's, suddenly becomes much more difficult and a rigorous task to complete because we can think about all of the different factors that might be affected when we're testing this hypothesis. So what are the steps in testing a hypothesis? First, we state the hypothesis to be tested. In other words, what is the assumption about the population that we have that we want to test? Second, specify what level of consistency with the data will lead to rejection of the hypothesis. This is called the decision rule. In other words, how confident do we need to be? How much information do we need to be to reject our current assumption? Next, we collect data and calculate the statistics to test the hypothesis. Number 4, we make a decision based on our test, based on the outcome of our testing of the hypothesis. Should the hypothesis be rejected or not? Number 5, take action based on the decision. What do we do next now that we've either supported or not supported our hypothesis? So let's talk about these one by one because they're a little bit more complicated than just as we stated so far. Number 1, state the hypothesis to be tested. Hypotheses are a pair of mutually exclusive and collectively exhaustive statements about some fact about a population. Mutually exclusive means only one statement can be true at a time. In other words, more than one hypothesis cannot be true. We need to state our hypothesis in a way where it's either true or not true. Collectively exhaustive means we're considering all possibilities. So these two statements are hypotheses because the truth is unknown. In other words, we don't know what the actual truth is, which is why we need to test it. H0 refers to the null hypothesis. Null hypothesis means if we have no information, we assume the null hypothesis is true. If we have information that shows us that the null hypothesis is not true, for example, our assumption is not true because the data doesn't match what we would expect it to be, then we would reject our null hypothesis and use our alternative hypothesis, H1. H0, the null hypothesis, must be stated in a precise way so that it can be tested against evidence from a sample. If the null hypothesis is rejected, we tentatively conclude H1 should be the case. We cannot accept a null hypothesis, we can only fail to reject it. In other words, if our data is supporting our null hypothesis, we need to be very careful about the language that we use when we explain this. Instead of saying that we're accepting the null hypothesis as true, we don't know if it's true or not. We just know that our data didn't say that it's false. So because of that, what we say is we fail to reject the null hypothesis. We're not saying that it's true, but we can assume that it's true because we have no other information. That's why we say the null hypothesis is assumed true and a contradiction is sought. Number 2, specify the decision rule. Before collecting the data, the researcher must specify how the evidence will be used to reach a decision about the null hypothesis. This involves setting a level of certainty that's required to reject the null hypothesis. We call this level of certainty our confidence level or our alpha level. Usually, 5% is used in many social science applications, including business and including other research. However, in some cases, we might need to be more certain about our hypotheses, such as, let's say we're testing a pharmaceutical drug. What happens if we're wrong about the dangers of that pharmaceutical drug? People could die. In that case, we might want to set our level of certainty to something much more difficult to test. In banking or finance, we also might want to be much more certain about what we are testing so that we don't lose a lot of money or lose a lot of money for the financial institution that we're working for. So in some cases, we might want to change this 5% level to something a little bit more rigorous in the case of danger or a lot of money is at stake or some other situation like this. The third step is collecting the data. The process of data collection can take a long time, but it's fairly straightforward using standard research methodology. Decision-making is when we compare the data that we've collected with our hypothesis, use the decision rule, and decide to either reject or fail to reject the null hypothesis. Based on that outcome, we need to take action based on the decision that we just made. This last step requires experience and expertise on the part of the decision maker. Appropriate action for the decision should relate back to the purpose of conducting the hypothesis test in the first place. So let's think about a very easy, simple, straightforward example. For example, suppose there's evidence at a trial that convinces a judge that the defendant is not innocent. Okay, that means they're probably guilty. What punishment should the judge impose? In other words, what decision should the judge make if the null hypothesis that the defendant is innocent is rejected? They're not innocent. What should they do? Another example, maybe something a little bit easier for us in day-to-day life, would be, let's say, suppose evidence shows that one of your classmates, or if you're not currently a student, maybe a worker that you work with, has plagiarized part of their work. What should be the penalty in your opinion? Well, it depends on how much evidence you have that they have plagiarized their work. And it depends on how severe, how serious that case is, right? So the hypothesis testing related to statistics is simply just testing whether we should reject or fail to reject our null hypothesis. The part afterwards, based on the action you must take, depends on the field that you're in. Let's talk about errors. There are two types of errors, type 1 and type 2 errors. Our ability to collect evidence can be limited by the tools, the time, how much money we have to collect evidence or data. So there's a possibility that we're making a wrong decision about the null hypothesis. We don't know the actual truth, we're testing the truth, so we might make a mistake. Consequently, our decision rule will be based on the levels of risk of making a wrong decision. As we discussed with a financial institution or a pharmaceutical company or some other high-risk situation, we might change our decision rule to make it a little bit more rigorous if safety or some other really strong consequence is at stake. We can allow more risk or less risk by changing the threshold of the decision rule. In other words, instead of using 5%, we might use 1%, or we might use 0.1% if we want to be really rigorous, that we're very sure about our testing of the null hypothesis or rejecting of the null hypothesis. There are two possibilities about the truth of the null hypothesis, and also two possibilities about the decision we make about the null hypothesis. Either the null hypothesis is true or false. In actuality, we may never know if it's actually true or actually false. However, those two cases exist. It's either true or false. Also, our decision is either to reject or fail to reject our null hypothesis. Because of that, in some cases, we make a mistake, we make an error. Type 1 error is when we reject a null hypothesis when it is true. In other words, our null hypothesis is true, but we reject it. We're wrong, and this occurs with the probability of alpha, the level of significance. This is also called a false positive. Alpha, if you remember, is the level that we set. So usually we set alpha at 5%, unless we're testing something that is a little bit more consequential, risky. Type 2 error is the failure to reject the null hypothesis when it is false. In other words, our assumption is false, but we don't reject it. This occurs with the probability called beta, and this is called a false negative. Beta is a little bit harder to calculate and depends on a few different factors. Specifically, it depends on what distribution you're looking at. It also depends on the level of alpha that we set directly, and it also depends on your sample size. In other words, alpha, type 1 error, we can directly set. We can set beta indirectly based on a few different factors. In order to remember type 1 error, false positives, and type 2 error, I think this little comic strip makes it a little bit easier. Okay, so let's say our null hypothesis is that you are not pregnant. Why would that be the null hypothesis? Because generally, most people are not pregnant at any given time. So if you are pregnant, there should be some evidence to show that. If there's no evidence, we might assume that a person is not pregnant, right? That is our base assumption, unless we have evidence to change our mind. So let's think about this example. If the null hypothesis is that you are not pregnant, there are two cases. Either you are pregnant and we're assuming that you're not, or you are not pregnant and we are correctly assuming that you're not. There's also two outcomes to testing this. Either we reject the null hypothesis and think that you are pregnant, or we fail to reject the null hypothesis and we assume that you are not pregnant. Now, if we make an error, we might make a type 1 error if we say that you're pregnant when you are not. In this example down here, this man is clearly not pregnant, but the doctor is saying you are pregnant. This is a false positive. In other words, they're falsely rejecting the null hypothesis by saying you are pregnant. Type 2 error is a false negative. In other words, you should reject the null hypothesis, but we didn't. So in this case, the doctor is saying you are not pregnant when the woman is clearly pregnant. The consequences of type 1 and type 2 error can be very different. The consequences of those two errors are quite different, and the cost is borne by different parties. So for example, let's look back at our example of the pregnancy example. If we make type 1 error, the doctor says you are pregnant to this man who is not pregnant, what is the consequence? Perhaps the man will not drink or not smoke or go to bed early to take care of his body better. It might cause emotional stress. He might be very stressed that he thinks he's pregnant. Type 2 error saying that this woman is not pregnant when she clearly is, what is the consequence of that? She might not stop drinking, or she might not stop smoking, or she might live a very unhealthy lifestyle, and that would have very negative consequences to the baby that she's pregnant with. So which consequence is worse? Is type 1 error worse in this case, or is type 2 error worse in this case? Analysts are increasingly wary of type 2 error, a false negative, failing to reject a false hypothesis. It can often result in more serious consequences. Obviously, it depends on what is the null hypothesis that we're testing, but in most cases, failing to reject a false hypothesis has more serious consequence, as we saw with the pregnancy example. It's more difficult to detect and quantify as well because it depends on a lot of different factors, such as the sample size, variability in data, the effect size, the level of alpha that we set. As I mentioned before, we cannot set beta directly, but we can set alpha directly. Alpha affects our type 1 error, beta affects our type 2 error. Since we can directly affect alpha, type 1 error is much easier to control. So we should be more wary of type 2 error in almost every case. What is the probability of type 1 and type 2 error? If we choose alpha, 0.05 for example, we expect to commit type 1 error about 5% of the time, 1 in 20 or 5 times in 100. Beta cannot be chosen in advance because it depends on alpha and the sample size and some other factors. So a small beta is desirable, all other things being equal, but it's difficult to affect it directly. All right, let's talk about decision rules and critical values. For a mean, the value of mu0, in Britain they call it mu0, I assume, is the hypothesized mean. The hypothesized mean is what we are assuming the mean of our population to be. So the value of mu0 that we are testing is a benchmark based on past experience or an industry standard or a target or a product specification. Basically, it's what we probably expect it should be. That's why we call it a benchmark. The value of mu0 does not come from a sample. The value of mu0 is our population mean. As I said in a previous video, it's very difficult to know the actual population. So, by using samples, we can test, does our sample agree or disagree with our assumption about that population? That's why hypothesis testing is so important. When testing a mean, we can choose between 3 different tests. A left-tailed test if we're interested in one side of the distribution, a right-tailed test if we're interested in the other side of the distribution, and a two-tailed test, meaning we are interested in just are we correct or not. It doesn't matter which direction we're correct or not in. We will discuss these a little bit more when we deal with some real examples. Let's talk about the decision rule. A test statistic shows how far the sample estimate is from its expected value in terms of its own standard error. This just means how far is our sample from what we expect it to be, probably our mu0, right? The decision rule uses the known sampling distribution of the test statistic to establish a critical value that divides the sampling distribution into 2 regions. We reject the null hypothesis if the test statistic lies in the rejection region. In other words, we calculate a statistic based on our testing sample. This includes the mean of that testing sample, the deviation in that sample, how big our sample is, the sample size. Using all this information, we test whether our sample matches our expected mu0, what we expect the population is. If that test statistic is too far away, and it lands into the rejection region, then we would reject the null hypothesis. If that test statistic is not in the rejection region, then we don't reject it. We fail to reject the null hypothesis. All right, so when do we use a one or a two-sided test? A two-sided hypothesis test, just means not equal, is used when the direction, greater than or less than, is of no interest to the decision maker. We just want to know if it's not equal. A one-sided test is used when the consequences of rejecting are asymmetric. In other words, one direction is more important than the other. Where one tail of the distribution is of special importance to the researcher, we would use a one-sided hypothesis test. Okay, so this doesn't make very much sense if it's the first time you're listening to it, so let's discuss it in a little bit more detail. If we think about our normal distribution, it looks something like this, right? And based on the empirical rule of that distribution, which we learned in a previous video, in other words, within one standard deviation above and below the mean, we have 68% of our data. Within two standard deviations, we have about 95% of our data. Within three standard deviations from the mean, we have about 99.7% of our data. So, using that information, we can test with a lot of accuracy how likely, how probable we are to get a certain outcome if we have an assumption what the mean of the population is. So let's say we set the mean of the population that we assume it is, our mu0, and we set that as the mean. Using that information, we can calculate how close our sample is to that expected value or how far away it is. So if we calculate our test statistic and find that it is very different than our mu0, it's very different than our assumption, we might reject our null hypothesis. We might say that our assumption is probably not correct if our test statistic is very far away from it. Also, it depends if our test statistic is very far away from it in a positive direction or very far away from it in a negative direction. There's a difference. If we're using a two-tailed test, well, a two-tailed test means we don't care whether that test statistic is above or below the mean. As long as it is far away from that expected mu0, we're going to reject it. It doesn't matter which direction. However, using a left-tailed test, that means we're only concerned if our test statistic is too far below the mean. Then we would reject our null hypothesis. In a right-tailed test, we're only concerned if that test statistic is too far above the mean, then we'll reject that null hypothesis. So we reject the null hypothesis if the test statistic is in the rejection region. In other words, if our test statistic that we calculate, which is based on the sample mean, the standard deviation of that sample, and the size of the sample, using all that information, taking all that information into consideration, if it's still farther than a critical value, then we would reject our null hypothesis. Okay, so let's talk about actually testing. Testing a mean. This example is testing a mean with a known population variance. What is the population? The population includes all of the possible subjects that you are making assumptions about, right? This is a commonly used example, the average height. Let's say you're trying to evaluate the average height of all the people in Korea. It's impossible to know this. So what would be the population variance? How much does that value vary from person to person? That's also impossible to know exactly. Instead, we could know a sample variance. We could take a sample of 100, 1,000, even 100,000 people. That's still not enough to know the population. So it's almost impossible to know the population variance, but for purposes of theory, theoretically, this example is how you would calculate it if we could know that information. Let's say I make an assumption that, I don't know, let's say I think that the average height of a person in Korea is 75 centimeters. Now, is that accurate? Probably not. Definitely not. But let's say that my assumption is that 75 centimeters is the average height in Korea. Well, depending on who I sample, I might get a different answer. On one day, I might sample 10 people, and I may have just by chance picked 10 very tall people. On another day, I might have picked people who are much shorter on average than the population mean. In other words, based on my sample, especially if I have a small sample, it can be affected by who is just randomly included in my sample. So when testing mu with a known sigma, with a known population variance, the test statistic is a z-score. What is a z-score? A z-score incorporates the sample mean, the standard deviation, and the sample size. Once we have collected our sample, we calculate a value of the test statistic using the sample mean and then compare it against the critical value of z. What is the critical value? If our sample statistic is more extreme than the critical value, then we reject null hypothesis. We will refer to the calculated value of the test statistic as z-calc, the calculated z-value. Here is how you calculate that z-calculation. We have our sample mean, so this is from the sample that I collect, minus what I expected about the population. And on the bottom, we have the standard error. The standard error of the sample mean is the known population standard deviation over the size of our sample. If the true mean of the population is mu0, then the value of a particular sample mean calculated from our sample should be near mu0. In other words, if our assumption of mu0 is correct, then we would assume that a sample taken from that population should be similar to the overall mean of the population. So if we assume that our test statistic is near 0, that our assumption about mu0 is probably correct. Okay, so what is the critical value? The test statistic is compared with a critical value. The critical value is the boundary between two regions, rejecting null hypothesis or do not reject null hypothesis. The critical value shows the range of values of the test statistic that would be expected by chance if a null hypothesis were true. In the critical value approach, what we're testing is whether our calculated test statistic is more extreme, either more positively extreme or more negatively extreme than a critical value. In a left-tailed test, we're only checking if our test statistic is more extreme on the lower end. On a two-tailed test, we're testing whether our test statistic is more extreme either on the upper or lower end. And in the right-tailed test, we're testing whether that z-calc test statistic is above some specific threshold. We call that threshold the critical value. A p-value approach is much more, let's say, useful and common. The p-value approach is looking at the probability rather than the critical value itself. The p-value is the probability of the sample result, assuming that H0 is true. Using the p-value, we reject the null hypothesis if the p-value is less than alpha. As I said before, usually alpha is 5%. So if we see a p-value, meaning a probability of getting that test statistic or one more extreme, if that p-value is very, very small, less than our alpha, then we would reject our null hypothesis. whether we use the critical value approach or the p-value approach, our decision will be the same. All right, so as I said, a known population variance is almost impossible. In most cases, the variance of the population is unknown, and sometimes it cannot be known. Because of this, we use a different distribution. We call that the t-distribution. Actually, it's called students' t-distribution. So the story is actually quite interesting to me. Students' t-distribution approaches a normal distribution given an infinite sample size. So if our sample size is really big, the t-distribution is the same as the normal distribution. But with smaller sample size, the distribution changes to be more platykurtic. The tails are thicker. There's more uncertainty about that distribution, reflecting the uncertainty of the small sample in representing the underlying distribution. So how was this t-distribution discovered? It was actually discovered by a researcher at the Guinness factory in Dublin, Ireland. It was first derived in 1876 by F. Helmert and J. Leroth, two German mathematicians and statisticians. However, William Seeley Gossett, an employee at Guinness, published in Biometrica under the pseudonym Student. The reason he used the pseudonym, he couldn't use his real name. Why? Because Guinness didn't allow the employees to use their real name in publications, particularly in research publications. Why? Because if other breweries knew that they were using this distribution, they would use it as well. So why would a brewery be interested in a distribution, specifically a t-distribution that's used across almost all statistics today? Gossett was using small samples to test the quality of raw materials. Specifically, I believe it was barley, at the factory he worked in, the factory being the Guinness brewery. So the normal distribution was not useful because he's using small samples of barley. He didn't want to use a lot of barley to test whether it's good or not, because a lot of that barley has to be used to make the beer. So he was using the t-distribution to test the quality using small samples, so he's not wasting a lot of those materials. So he can make more beer. Ronald Fisher, very famous statistician, called the distribution students' distribution, and he made it very popular. That's why we call it students' t-distribution. So what does the t-distribution do? What's the purpose of that story? The t-distribution is like a normal distribution, but if we have a small sample, we're very uncertain whether that sample is following a normal distribution. Instead, it's following a t-distribution, which is more uncertain because it has fatter tails in that distribution. So, if the population variance must be estimated from a sample, the hypothesis testing procedure is modified. There's a loss of information when S replaces sigma. What is S? S is the standard deviation of our sample, and sigma is the standard deviation of our population. And it is no longer appropriate to use the normal distribution. Instead, we use this t-distribution. The t-distribution changes depending on how big our sample is. If our sample is very small, it looks like this red line here. So we see that the tails are much fatter on the ends. However, the bigger our sample gets, the more that it looks like this normal distribution curve, which is this gray curve in the back here that goes way up here, and then it goes way down here. In other words, our tails are lower, meaning there's less uncertainty. There's fewer values that are far away from the mean. So how do we calculate this? We use our sample mean, same as before. We use our hypothesized mean. This is showing the difference between our sample mean and the hypothesized mean. If our null hypothesis is actually true, then our sample mean should be very similar to our hypothesized mean. But it's probably not exact because there's some randomness involved when you're picking a sample. our sample standard deviation is used. So this is the standard deviation calculated from our sample. And n is our sample size. So we can get all of these values, the sample mean, the sample standard deviation, and the sample size from our sample. The hypothesized mean is what we already expect about our population. Therefore, to test our assumption about the population, all we need to do is get a sample. The smaller sample we have, the more uncertain we are about that sample, so it becomes more difficult with a smaller sample to reject our null hypothesis. Okay, let me make one more note here. It is not proper to use the student's t-distribution nor the normal distribution when testing a proportion. A proportion is a little bit different. Why? Because your proportion cannot be more than 100%, nor can it be less than 0. When testing a proportion, your proportion, for example, let's say that my cafe has 80% market share. Well, I can't have more than 100% market share, and I can't have less than 0% market share. So in other words, a proportion is limited because it has to be between 0 and 1. And also, we don't have a standard deviation of that proportion in the same way that we do with a normal distribution. So our z calculation is a little bit different when dealing with a proportion, so just keep that in mind if you're testing a proportion. All right, so that is one sample hypothesis testing. In the next video, we're going to talk about 2 sample hypothesis tests. All right, thank you. So that was a discussion about 1 sample hypothesis testing. I know it can be a little bit confusing the first time you hear it, so I recommend to look at the next video and also to review the video where we're using R to solve some problems about hypothesis testing. That will be in a future video. I hope you watch the next video in this lecture series, Applied Statistics Using Programming, and I hope to see you in the next video. Thank you, and see you again soon. Also, those 2 possibilities regarding the decision made about the Why is this one so hard? Type 2 error, what? Type 2 error